Graph or tree is another data structure that I struggle with. Therefore, I'm going to explain a problem that involves solving graphs. The prompt goes, write a function that determines if a path exists between two vertices of a directed graph. The function will be returning a Boolean. The graph will be represented as an object, each of whose keys represents a vertex of the graph, and whose value represents all vertices that can be reached from the aforementioned key. In the example below, which is this object right here, there is a connection from vertex A to vertex B, and a connection from vertex B to vertices C and D, but not a connection from vertex B to A. We'll be covering directed acyclic and cyclic graphs here. Cyclic graphs mean one of the nodes on the graph can cycle on itself. Example 1 here is a directed acyclic graph. A is pointed to B, and B is pointed to two vertices, both D and C. C is pointed to D, but B is not pointing back at A, and D is pointing to nothing. The graph object is a data structure called adjacency list, which is the graph object here. Multiple vertices are stored in an array, and when the node is pointing to nothing, it's represented as empty array, which you can see here. So let's see, do we have a path between A and B? So A is pointed to B. Yes, there is a path, so we return true. Do we have a path between B and A? No, because B is not pointing back at A, so we return false. Do we have a path between A and D? So A is pointed to B, B is pointed to D. So yes, there is a path between A and D. Therefore, we return true. So do we have a path between N and itself? The answer is no, because this is an acyclic graph. A is not cycle on itself, so we return false. Example 2 is a directed cyclic graph. It's the same concept as example 1, except A can cycle on itself, which creates a loop. So let's see, if we run the function, do we have a path between A and itself? Yes, we do, because it's a cyclic graph, so we return true. Is there a path between C and itself? So C is pointed to R, R is pointed to A, and A is pointing back at C. So yes, there is a path between C and C, so we return true. Is there a path between R and S? R is pointed to A is pointed to C, C is pointed to S. So yes, there is a path, we return true. But there is no path between S and A because S is pointed to nothing. Both breadth first search and depth first search have the same time complexity. And I'll be focusing on the depth first search today. The difference between the two algorithms in this problem is that breadth first search will finish in traversing the nodes pointing to vertices in the array before it moves on to the next vertex, hence level by level, versus depth first search will traverse on one of the vertices in an array, continue traversing that way until it reaches the leaf that points to nothing, hence branch by branch. Let's take a look at the function. We'll be using recursion here, and it's helpful to create a visited map object as either an additional argument or a global object to track visited nodes. Why? Because we can leverage its properties and values to determine if we need to keep going. Let's now break it down. If the node is pointing to nothing or empty array, we return false. Every time we traverse the graph, we create a new property in the visited object and mark it true for being visited. This is useful when we do the recursion here. We then move on to the vertices of the starting node and check if one of the vertices is a target. That's what array.sum is for. So if it is, we return true. If not, but the vertex has not been visited, we don't stop there. We want to keep traversing on the yet to be visited node to determine if any paths exist. This is where the recursion happens. So for each recursion, we use the yet to be visited vertex as a starting point and mark it visited until it hits one of these conditions. And we return the final result. If I run the function, you can see that the visited map becomes more complete with each recursion. The time complexity of this solution is O of V plus E, where V is the number of vertices and E is the number of edges, because we need to visit every node to determine if any path exists. The space complexity is O of V plus E with additional auxiliary space of O of V for the visited object. There's another data structure we can use in place of adjacency list. It's called adjacency matrices, where we mark true or false for the nodes that have pointed vertices. So if we want to read this matrix here, A is pointing to both A and C is pointing to S and R. Sn pointed to nothing, and R is pointed to A. While adjacency matrix is easy to implement, its time complexity for traversal is O of V to the power 2, because for each vertex, we're checking if it has pointed vertices. So in JavaScript implementation, this is what it looks like. If we have a nested loop that iterates over each element, for each array, which represents a vertex, we're checking each element inside the array. So overall, adjacency list is better in terms of time complexity. I hope this video is helpful for better understanding graphs and trees. See you next time.